So yeah, I do want to talk about this idea between water and energy, and I think the last couple of speakers did a great job of telling us how important water is, globally, locally, and how Nicholas has talked about how it ties into our history. But in the modern world, we live and drive off of a lot of energy use, and water plays a very integral role in terms of how we how we use and generate energy. So I do want to talk about that. So we live, I guess, in some sort of functional modern society. We can debate how functional we are as a society, but that's a different question for another day. But we live in a functional modern society, which means, as an engineer, I look at systems where things come in and go out, right? So in a functional modern society, we, have lots of inputs coming in: water, energy, food, agriculture. Lots of these connected by materials, lots of cross flows to bring things to our society. And the focus for today, and I'll focus on this interrelationship here between water and energy. And as an output from this society, we look at, economic development, health and wellness, sustainability for the environment, security needs, and all of these are, I guess, the prime outputs that we get out of our society. So, just to set the stage for our water energy focus, they are in many ways very interdependent. So what do I mean by that? Well, very simply, we need energy and power for producing. Energy and power production requires lots of water. Water production and use requires lots of energy. So what would be some examples to do this? We get most of our electricity from a variety of forms, which requires use of water in lots of different ways. It could be for cooling, could be for hydropower, turning the turbines, industrial mining and extraction, fuel production, emission controls. All of these things require water, varying amounts, but lots of water usually. If you want to move water for a settled society, we need to pump it from the source, move it around, treat it, some conditioning for disposal, and perhaps even reuse. And usually these are in two forms: either they occur as surface waters or as groundwaters. So let's focus a little bit on the United States and see what we do with our water, right? So this comes from a report that was done in about 2003, 2004, and that's really the last time a federal report came up with sort of looking at water consumption and withdrawal in the United States. So based on this data, that's a little bit dated. At the time, approximately 40% of the water was used for power generation in the United States. We used 8 to 10% of the water for industrial mining needs, another one for domestic use, 10% or so, and then agriculture was the other 40-odd% block that we used for water, right? And the costs that are associated with harvesting this water, processing this water, using this water are highly source dependent. So it really does depend where you get the water from. And I won't go too much into detail about that, but that's something to keep in mind. So as a sort of benchmark, or thinking about how much water we withdraw from all sources, it's on the order of about, per year we get about 124 trillion gallons of water in the United States, which is equivalent to about the yearly outflow of the Mississippi River. And of all that, 40% goes in power production. So it's really the same problem whether you talk about water or energy. Why? Because if you account for the industrial use, which includes mining and refining of fuel sources for power generation, in the United States, that's the largest water consuming sector. Right? It goes beyond even what agriculture would consume. If we use coal for power production instead of natural gas or nuclear, we increase the loss rate of water by approximately 1/3. If we go to hydrogen from coal, as many technologies are saying, hydrogen is a cleaner fuel, we increase the water loss by about 2 times. And this is not withdrawal, which is we just don't take it out, it's consumptive, we just put it up the smokestack. Right? So this is water that we're not necessarily getting back. Or it will come back, I guess, as rain eventually. And but there's lots of lossy water use here, power use. There's lots of talk about new sources of energy, renewable sources of energy. Looking at biomass, syngas, hydrogen-based fuels. If we do transition to a lot of these, which is happening, we do need to get lots more water because we'll double the current use per gallon of water. So for example, corn ethanol requires 4 to 6 gallons of fresh water to get every gallon of corn ethanol. That's just refining. It does not account for the water that goes into growing the corn in the first place. That's about 1,000 times more than that. So, the amount of water we need to meet some of these energy uses is tremendous. So, if we incorporate all this new energy in the system in our functional societies, we need the water withdrawals to go about 2 orders of magnitude higher, which means we need about 100 times more water than what we have currently. So, conservation is a great idea. I don't think we can go anywhere without that. But even if we ration half the water, right, we at most get an increase in our supply by 2 times. We need 100 times more water. So conservation alone is not going to do it. There's just no way to do it by conservation alone. So, what does the impact truly mean if we don't have enough water? How does it impact our energy? So if we don't have enough water, it's going to be near about impossible to meet the demand for energy that comes from a growing population. Okay? So I'll talk about this population aspect a little bit later, but that's something to keep in mind. It's going to be extremely challenging to transition over to a hydrogen economy because any way to produce hydrogen as of now requires a lot of water. So no water, no hydrogen. Our ability to use biomass or any fuels that are derived from clean coal, again, without water, that's not going to happen. Same thing with carbon sequestration. It requires lots of water to capture all that carbon and this, coming out of the smokestack. Being in Ohio, we are fairly well exposed to shale oil and gas, and across the United States, we are really the dominant source of shale oil and gas that exists. But we can't use it without proper ways to use the water in the first place and then eventually manage the disposal. Because there is a lot of toxins and contaminants that exist in the flowback and produced water, and there is really no way to manage it. The best way right now is in Ohio, which is just dig a deep enough hole and put it in there and hope it never comes back out. And Ohio is, I think, the only state that has not banned deep well injections yet. Every other state that had started drilling for shale oil and gas has now banned deep well injections. So there really is no way. But, this is a great source of energy, so we need to figure out ways in which it can be done better. So plug-in vehicles are a great idea. They are relatively clean burning, which means at some point we do have to charge them, right? We do need to go and plug them in to get the battery to go and do all of those things, which means our electricity demands are going to go up. Electricity, where does it come from? We burn coal and natural gas, and so, for that, again, as we talked about, we need more water. So we really can't use plug-in vehicles unless we have more water to produce more power. So, was it scary enough? Probably not. So let's see, can it really be worse? Population growth is approximately 1% a year, has been so for last several decades. One of the other problems that has been happening is the shift in population, which arises because of economic mobility, social mobility, and it puts lots of pressure on both water and energy as well as food demand. So what that has led to is local problems are growing. Water as a resource is a global resource which is used locally, right? So lots of local problems are growing. Logistics for distribution, management, and maintenance of infrastructure, supply lines are just, beginning to get difficult. It was talked about in terms of, how unsustainable really is in terms of overpumping of ground aquifers, and that really is not the solution. It's a great resource that's available, easy to get to. Technology exists to get it out, but it's an unsustainable path forward. The complete nexus, really, I'm just focusing on water and energy, as in you throw in food, and we have the complete trilogy here. So that's really the complete nexus to think about. Then comes the problem of contamination of waters from all the activities that we deal with. Right? There's cross-contamination of both surface waters and ground or aquifer waters growing. The most easy solution so far has been dilution, right? You take a pot of contaminated water, add clean water to it till the solution's dilute enough that we don't have to worry about it. We throw it back out in the river, we're happy. That's not going to be sufficient anymore, especially because there's lots of byproducts of industrial processes that are beginning to show up, emerging contaminants that are beginning to show up, and what that will drive is need for new technology. And along with that comes this idea that there's finite and always increasing costs of energy, because all of these processes that require treatment of water, cleanup of water, need energy. Right? So there is again the tie-in between water and energy. We can't really do one without the other. There's a highly centralized system, right? There's a utility somewhere that focuses on getting water from a source, cleans it up, sends it to all our houses, we flip on the faucet, out comes nice, clean, fresh water. Right? And these centralized systems are very capital, energy, and material or chemically sensitive, intensive. And these new systems that we are developing for growing populations, if we continue on that path, are very quickly going to become unsustainable. And let's throw in the problem of climate change, with some snowpacks and glaciers melting. Most rivers that historically would not run dry, even in low rain months, are beginning to show up as the water flows are declining significantly. And that's really a big problem given how the population is growing. Most population historically has been centered around a major water source. Right? And if these begin to dry up or start having fluctuations in their levels, those populations are going to migrate or come up with different ways of dealing with that. So it ties back into this first idea, not just population growth, but also population shifts. Okay, so it can be worse. So, let's see what, I'm an engineer, so, as I was taught in the freshman year, all we have to do is, if there's a problem, you're an engineer, you go figure out how to solve it, right? So we now have a problem, how do we solve it? So, we thought about it for a long time, so, there may be suggestions that we can learn from nature, and as well as nanotechnology that can help us. So why is that the case? I think, in my view, nanotechnology provides some unique opportunities to deal with the water problem. And the reason for that is that it really provides us with fundamental tools in terms of how matter and fundamental building blocks of matter interact with each other. So we can look at those, learn from that, and then use those tools to harness the very fundamental structures out of which matter is built. And if we can do that, we can recreate or build entirely new systems, and that really begins to take place because nanotechnology works at similar length scales as fundamental laws of nature. Right? So things like flow of charge and electricity, things that are very basic in terms of our environment, that's where nanotechnology works. So we can work at the same length scales where physics takes place, where natural laws govern phenomena, and then begin to generate solutions based on that. So that would form the basis for new technology or new innovative approaches to dealing with water issues. Okay. So what can nanotechnology really help with? So one could be thinking out sort of looking at a pie in the sky idea, that we move away from our centralized chemical mixer systems, go to systems where we only use chemicals as and when they're needed. We don't need to use one shoe size fits all approach for our treatment facilities. We can start to view wastewater as resource water, because wastewater contains lots of not just chemicals but also nutrients, ammonia, phosphates, which are a definite finite resource and will run out of. So we can recover a lot of these materials from the wastewater and then reuse it. So in my view, wastewater truly is resource water. We could use less input of external energy in our system. We could increase the use of biologicals and renewables for generation of energy. We could look at solar and wind energy. We can look at energy generation from waste, including wastewater, biomass. There's lots of different streams that can help do these things. And then finally, I think another area where nanotechnology can contribute is interfacing very well with biology, because fundamental biological processes inherently are again at the nanoscale. They are driven by nanotechnology. So we can learn from nature in terms of detecting how viruses and other media interact to see if we can develop smart sensors, biologically derived sensors. Remediation of solids and wastewater. There's lots of learning opportunities here to go with these approaches. So what I'm going to do now for the next, remainder of this talk is give you 3 or 4 examples in terms of how nanotechnology has been used to address some of these challenges, specifically in our lab at Ohio State. I'm going to use one example from our side, but specifically, most of these are from here. Example of salt desalination, of getting salt out of seawater. And we've done a lot of study on this. We looked at this and we found that the current desalination methods are extremely energy intensive. So here's a table we put together. The main idea to look at is that we take lots and lots of energy to produce fresh water from salt water. That's the main idea. So how much energy do we really consume? If you look at the theoretical limits, depending on what system you're working with, you're anywhere from 4 to 100 times higher in energy consumption than what theory predicts you should be at. So there's fundamentally a lot of space to develop new technologies to improve and build systems that would not be as energy intensive. So how do we do that? Well, so there's several examples of new technologies that are being developed, and one of the systems borrows from biological systems. Biological systems are great at allowing me to talk and move muscles at the same time, right? And this is all done because they can control salt motion through the system very quickly, very rapidly, in a very efficient manner. So we say, okay, how does biology do this? Because it consumes very little energy, operates at the nanoscale, and moves these sodium and potassium ions very efficiently. Right? So we look at that, say, okay, how do we do that? So here's 2 examples. This one's a chip scale system which produces a fraction of the energy cost. Takes seawater, gives you nice clean water coming out. This is being developed at MIT. This is an example of a device we've built which uses slightly different physics with embedded charges that allows us to control how salt moves in little pipes. So you say, okay, how little are these? Well, we make them with the same process as we make computer chips. We can stack millions of these together in a relatively small area. And they consume, I'd say, anywhere from 1/10 to 1/20 of the energy that's needed by traditional methods. So we can drop the energy consumption significantly for these things. Another example will relate to this idea of resource water and how we can really get energy out of wastewater. So I'm going to first discuss what is actually in our wastewater. So in the United States, we have a lot of dry solids. I mean, that's a lot of dry solids in our wastewater, which translates to several billion kilowatt hours of electricity equivalent if we were to harvest all of these dry solids. So, currently most municipalities don't really do much with this biosolids. It's either treated and applied to land, burned, or hauled away and stuffed on the ground. There's only few that may do a few other things with it, but for the most part, we don't really do a whole lot with these biosolids. So going back a few years, you compare the total electricity generated in the United States was on the order of about 10 to the 18th joule, which is just about 10 times more than the amount of energy contained in the solids in all of wastewater. So it's not that far away. Energy content of wastewater, if you think about it in actual percentages that way, then is that about 2% of all electrical demand can be met by wastewater, which would nearly be equivalent to combining all renewable sources like solar, wind, biomass that we do today. Right? So you could replace all of that with energy content of wastewater. So we developed this system in our lab, where what we are doing is we take waste coming in, we digest it anaerobically, move it to a system where we harvest both the biogas that comes out and ammonia that exists in the wastewater streams. We did a lot of analysis on this system, and what we found was that if you get the ammonia out and convert it to hydrogen, ammonia contains lots of hydrogen, from the wastewater, along with the biogas that you harvest, which is largely natural gas or methane, you get up to a 20% enhancement in total energy recovery, right? As of now, we don't harvest the ammonia. Most of that ammonia is treated or is not accounted for in terms of how we would use it as an energy resource. Ammonia is a very valuable industrial chemical as well. So, this is a modular system. You don't have to get the ammonia out and convert it to hydrogen. You could just stop, get the ammonia, use it directly for any number of industrial needs. So there's lots of energy savings that are already built into existing systems that we can use. As a final example, I'm going to talk about high efficiency microbial fuel cells. So there's about a half a dozen or so special species of bacteria that exist in nature. What they do is they eat waste and produce electricity. So that's kind of special. So we said, okay, what do we do with this? And so we looked at developing systems. Other people have done this as well. Is to put these together in the form of a fuel cell, and then say, okay, we're going to extract some energy from this waste stream by using these bacteria. What we found was that while this technology is very promising, most systems that exist out there are very low efficiency. So they don't do very well. So we looked at, again, biology and nanotechnology to give us some inspiration, and we looked at two structures, one in sea corals and cow rumen, because bacteria like to grow very well on these structures or these types of structures. So how can we exploit what nature already does to engineer a more efficient system? And to go with that, we've started using some new materials we've developed, and we found that the efficiencies can be increased significantly compared to where we've been with the microbial fuel cells for some time now. So, with that, I'm going to wrap up and talk a little bit about what we can do for our great blue planet when we look at both water and energy together. And I think there's lots of opportunities for us to look at lots of tools working together. The first is focus on basic science, work with conservation, lots of room to develop public-private partnerships to help both of these goals of working with basic science and conservation, which will eventually lead to economic opportunities in lots of different markets and areas. To make sure that our systems stay sustainable, it also gives us lots of opportunities, and hopefully I've highlighted that through several examples, that for technology innovation, systems development, implementation to all kinds of infrastructure. It could be centralized infrastructure, point of use infrastructure. There's lots of opportunities to do that. And then finally, we may have to create new kinds of infrastructure if we want to go at targeted populations where central infrastructure may or may not exist. So with that, I do want to emphasize once again that water and energy are really a coupled problem. We can't really solve one without the other. And we should address this by bringing in what I would call lots of stakeholders, right? There's a variety of populations at all levels that are affected by this. And I think if we bring people together to do that, that's the one way to address or begin to address some of the challenges. I do want to thank some of my collaborators and students, and of course the federal agencies who shine, the funding dollars on us. Without that, we would be nowhere. Of course, thank you to all of you for being here, and I'm happy to take any questions.
I know that after this great talk about technology, you're not a policy expert, but I'm wondering about what your observations of the policy priority, the funding priorities of agencies in the U.S. and elsewhere in the world with respect to desalination versus more efficient use of fresh water, current fresh water technology. Like, where are they going on?
So, I mean, I guess it depends on what agency you're looking at, right? So, in the United States, the research funding and development structure is driven by really two groups, right? So, one are what we call mission-oriented agencies. So, those would be like the Department of Defense, National Institutes of Health, which cater to a specific mission for the national public. If you look at agencies like NSF, which is really the only agency in the country that does sort of unsolicited basic science, has a relatively small budget. NSF does not have an explicit Office of Water or looking at water as a problem. So you have to go and say, okay, where would some research fit and deal with that? EPA does have an Office of Water, but they do most of their research in-house with some collaborations. The mission-oriented agencies, if there's a specific need, they will sponsor large programs. But again, that's dependent on their needs and if it meets one of the goals for their missions. It's not a global problem that they are willing to address and invest in.
Go ahead.
A little question regarding the filtering using sort of microchip in sea water. And what is the current flow rate for filtration?
It's about, on the order of about, you can get about a soda can of water in maybe a couple of minutes.
Okay,
Yeah, for about soda can worth of water, so about 300 milliliters.
What are some of the hotspots for nanotechnology in the world right now in application to water?
Where are the hotspots?
Yeah.
So there has been some development. So I guess, in the United States, there have been really three centers. So Ohio State, Illinois, and MIT have been the three main drivers. There's been some work done out in California, but not a whole lot on that. Worldwide, there has been a lot of work done in Europe. There's some work that's beginning to take place in Japan. One of the unlikely places has been Saudi Arabia. And while the work is actually not being done in Saudi Arabia has been funding a lot of research, primarily at MIT, some in other places, and in some institutions in Europe. And they've been driving a lot of these research projects because they see a very fundamental need for water, not just for use as living in a desert area, but also for their energy needs. And there has been significant investment done through those groups.
When you're talking about the biomass from our wastewater treatment plants that could translate into energy, is that a calculation based on the carbon, or is that is that actually how much we could get out? You know what I mean? Do you
Yes.
have the technology to get that out if you wanted to?
It depends on what form you want to get the energy out in. So, to the first part of your question, yes, it does account for the carbon content of the waste stream to calculate the energy. So many of the systems will actually take in, or the power plants will take in the biosolids and just incinerate them to get energy out. So that's one way to look at it. The other way is that use of microbial fuel cells. Typically, those are not being used at an industrial scale right now just because they're so poor in terms of their efficiency. So that a lot more work needs to be done to figure out how you run them at efficiencies that would be comparable to a standard power plant. Because without that, AEP is not going to invest in setting up a power plant based on microbial fuel cells.
But like an anaerobic digester is something that makes a fuel that you then use.
Correct.
Is that right? And
Correct.
that's the difference between that.
Correct. Correct. So the difference is that an anaerobic digester will produce a fuel stream, which can be used for whatever we want to do. A fuel cell will take the waste, the bacteria will eat that waste and produce electricity directly.
And which is more efficient in theory?
Well, I mean, we really can't compare because they are different. But as a system, as of now, the anaerobic digestion is more efficient because there's been more work done. People have optimized lots of those systems. Microbial fuel cells is a very native, or I guess, nascent technology.
Thank you very much.